Every single day there's a gigantic nuclear fusion reactor hanging up in our sky, just bathing our planet in a frankly incredible amount of energy. I'm talking about the sun, of course. But with all that raw power shining down on us, how much of it do we actually manage to capture? Let's take a closer look.
Okay, just get a load of this number. 173,000 terawatts. That is the constant fire hose of energy the sun is spraying at our planet every single second. It's a number so huge, it's kind of hard to even wrap your head around it. So let's try to put that into perspective. That constant stream of energy, it's 10,000 times more than what our entire species uses. I mean, everything, powering all our cities, all our homes, all our industries, that's just a tiny drop in the ocean compared to what the sun gives us, completely free of charge.
Which naturally leads to the big question, right? The one we're here to really dig into. With all that free energy just sitting there for the taking, could we really run our entire planet on nothing but sunshine?
Well, to answer that, we've got to go inside those solar panels we see everywhere, because the real magic is happening on a scale you just can't see. We need to zoom in, like way, way down to the atomic level, to find the tiny engine that makes this whole thing work.
The key ingredient here is silicon. The stuff sand is made of. It's the second most abundant element on Earth. Now, silicon is this really special material called a semiconductor. That means it's not quite a metal that always conducts electricity, and it's not an insulator that blocks it completely. It's right in that sweet spot in between. And honestly, that's its superpower. And here's where the genius comes in. A solar cell isn't just one pure chunk of silicon. It's more like a sandwich, made of two slightly different types. On one side, you have what's called N-type silicon. It's been tweaked to have a bunch of extra free-roaming electrons. On the other side, you have P-type, which is designed with these empty spaces, or holes, that are just waiting for an electron to pop in.
So when you press these two layers together, something really cool happens right at the border. It's called the P/N junction. Those extra electrons from the N side can't help themselves. They jump over to fill the empty holes on the P side. And this tiny little migration of charge creates a powerful, permanent electric field. The best way to think of it is like a one-way street, just for electrons.
And all of that careful setup brings us to the main event, the photovoltaic effect. Here's how it goes down. First, a particle of sunlight, a photon, slams into the silicon. If it hits hard enough, it knocks an electron loose, leaving a hole behind. Now, without that electric field, the electron would just fall right back into the hole. But this is where our one-way street comes in. That field instantly shoves them apart, pushing the electron to the N side and the hole to the P side. Finally, we just add some little metal contacts to collect all those freed electrons, send them flowing through a wire to power, say, a light bulb, and then guide them back to the other side of the cell to fill another hole. That continuous loop, that flow of electrons, that is electricity.
So that's the amazing little process happening in one single tiny cell. But how in the world do we get from that microscopic event to powering an entire house? Well, that's all about scaling up.
You see, a single silicon cell all by itself only produces about half a volt, not enough to do much of anything, really. But the magic is linking them together. You wire up a dozen or so into what's called a module, and suddenly you've got enough voltage to charge your phone. Then you connect a bunch of those modules together into an array on a rooftop, and boom, you're generating enough power to run your whole home. And this just shows you one of the most beautiful things about solar power. The only moving parts are the electrons themselves. There are no gears to grind, no fuel to burn, nothing to wear out. The electrons just go back to where they started. This is why solar cells are so incredibly tough and can last for decades.
Okay, so the science is beautiful, the tech is durable. So what's the catch? Why isn't everything solar-powered already? Well, this is where we hit the reality check. There are some big logistical hurdles we still need to figure out.
So, the biggest, most obvious problem is that the sun isn't exactly consistent. Some parts of the world are a lot sunnier than others, and even in the sunniest places, it gets dark every single night and you have cloudy days. To go 100% solar, we'd need massive battery systems to store power for those dark times, and probably a global grid to move electricity from the sunny side of the planet to the dark side. And on top of all that, there's the issue of efficiency. Take a look at this. The average commercial solar panel you can go out and buy today is only about 15 to 20% efficient. That means a staggering 80% or more of the sunlight that hits the panel doesn't even get turned into electricity. Why?
Well, some of it just reflects off the surface, and some of the photons just don't have the exact right amount of energy to knock an electron loose. Pushing this efficiency number higher is one of the holy grails of solar research.
Okay, so keeping those challenges in mind, the need for storage, for distribution, and for better efficiency, let's circle back to our original question and see if we can finally get a realistic answer.
Let's just be really direct about it. Using only the solar technology that exists right now, today, could we actually meet the entire planet's energy demands? And the short answer, which might surprise you, is yes, we could. The science is solved. The challenge isn't about possibility anymore, it's about priority. It's an engineering problem, an economic problem, and a political problem. It would take a monumental investment and, of course, a whole lot of land. But how much land are we really talking about here? Well, estimates vary, but to power the whole globe, we'd need to cover an area in solar panels somewhere in the hundreds of thousands of square miles. And that sounds impossibly huge, I know. But then you look at a map. The Sahara Desert by itself is over 3 million square miles of largely uninhabited, sun-drenched land. Suddenly, that impossible number starts to sound surprisingly doable.
And we have to remember, for over 1 billion people who don't have access to a reliable electric grid, solar isn't some far-off future idea. Especially in sunny developing nations, it is already the cheapest, safest, and most practical solution. It's happening right now, today. And the technology is nowhere near done evolving. We're seeing these incredible innovations like floating solar farms on reservoirs and lakes, which completely sidesteps the whole land use debate. The creativity in the space is just relentless. So the takeaway is really this. The raw potential has always been there, hanging right in our sky. The technology to capture it is here now, and it's getting better and cheaper every single year. The question is no longer if we can power our world with the sun, but will we? What needs to change, not in our labs, but in our priorities, to make that future a reality?